So Prashant is away, so I'm guest lecturing today. So I'm David Irwin. I'm a professor in the ECE department here at UMass. Has anyone here ever taken a class that I teach? No? Okay, good. Excellent. All right, so today Prashant gave me the topic here to lecture on, which is data centers and cloud computing, which luckily is my research area, so one of my research areas, so it's a good topic for me. Yeah, just by the way, where are you guys in the class? Well, actually, what class is this? Distributed operating systems, okay. And then what did you guys talk about last class? You don't remember what you talked about? Class. It was on Friday, right? Say again?
Communication method oriented transmission.
RPCs, okay. What are RPCs? Remote procedure calls? What is that?
You can call a function on different system from your system.
Okay. And what kind of, did you guys talk about any specific implementation of RPCs? No. Well, what are the common, what's like a common RPC protocol? Well, what are the parameters to RPCs? What kind of, are the parameters to RPCs limited in any way?
You can't pass
By reference is not
you
possible.
can't pass by reference.
Right, yeah, you can't pass by reference, yeah. Can you pass arbitrary objects?
I thought you should.
Well, at least the sender and the receiver would have to know about the object, right, and be able to decode the object into a set of primitives, right? Did you guys discuss that, or? Yeah.
Yeah.
Okay. Does anyone know the kind of most common RPC protocol, or not? Maybe not. Yeah, let's say the most common.
Java RMI.
Say again.
RMI.
Java RMI is one.
Yeah.
It's built into Java, right? But it's Java specific.
Yeah.
So you have to code in Java. What about an application agnostic RPC protocol? I mean, I have no idea what you guys discussed, so I don't know if you have a basis for this. So SOAP, right? So SOAP is an application agnostic RPC protocol. I mean, I don't think you'll be tested on this because Prashant doesn't know what I'm talking about it. Simple open access protocol. It supports objects, right? So that includes a web services definition language that specifies what objects can be defined in the RPC, and how the sender and the receiver both can decode those objects, encode and decode those objects, and how they boil down into some set of primitives, right? All objects boil down eventually into the state, ints and bytes and strings and whatnot. Yeah. So yeah, RPCs, they make stuff available via the web. Actually, it'll hook into cloud computing a little bit, because a lot of these cloud computing platforms we talk about today, they expose their functions via RPCs. So we'll talk about Amazon, right? So all of Amazon's functions, well, at least they used to be exposed by RPCs, right? So if you wanted to request a server, there would be an RPC call that you could hit to say, like, call a function get server. Actually, Amazon doesn't use SOAP anymore. They deprecated SOAP as the RPC protocol that they used to implement their infrastructure a year and 3 months, December 2016, I think. Any guesses as to what they replaced it with, and what is kind of REST? Yeah, REST is not an RPC, but it's a lot kind of like an RPC, very much like an RPC. Did you guys talk about REST?
Yeah.
In the context of RPCs? No, in a separate context, right? Yeah, right. So REST is a philosophy. It's not an actual specific implementation of something. There's much more to it than RPCs, but effectively it is overloading the HTTP protocol to affect arbitrary state manipulations on remote resources. And oftentimes you can frame RPCs as state manipulations on remote resources. Yeah, so a lot of people are, instead of using SOAP, are using now REST, or building RESTful services. All right, so okay, so RPCs. I'll mention some RPC stuff in here where relevant. So data centers are large server and storage farms with thousands of servers. Often, actually, there are different sizes of data centers. The large-scale data centers run by Google or Facebook, probably have now in the millions of servers, certainly millions of cores, hundreds of thousands of servers, not just thousands. Many terabytes of data, petabytes of data. Generally, data centers are distinguished from high-performance computing centers. Does anyone want to hazard the guess as to what the distinction between a high-performance computing center might be in a data center?
To store data.
Yes, the data. Right, so high-performance computing centers, to some extent, you might, those two terms could be thought of like interchangeably, but to the extent that there is a difference, you think about high-performance computing centers being operated and managed by scientific facilities, right? The Department of Energy, various academic institutions, but not computer science, domain sciences that actually use computers for something useful, that aren't just like studying computers. And those facilities tend to focus much more on computational workloads that don't, historically, that don't read and write as much data. And so it used to be the case that, you'd have these large, massively parallel, highly specialized mainframes. They still exist, that would run complex computational simulations. So like you can think about weather forecasting, right, where you're taking information, you're running these kind of complex forecasting models that have to solve, these kind of arrays of differential equations. So very computationally intensive and kind of been around for a long time. Data centers, in contrast, you think about being more associated with enterprises like Google or Facebook or companies that are collecting and processing lots of data, right? So they collect lots of data about you, at Google, like your ad preferences, and they want to mine that data to like learn about you so that they can target better ads for you. So very data intensive, and not as much computationally intensive, right? So the bottleneck is kind of the reading and the writing of the data. They're not always solving kind of large sets of differential equations, right? Now, obviously, those are just kind of general impressions. Both of them are kind of like meeting to some extent in that HPC centers are becoming more data-driven, and data centers are obviously, do more than just kind of read and write data and manipulate data. They also do intense processing, right? But in terms of kind of the general applications, that's kind of how it breaks down. So here in UMass, right? So there's the Holyoke Data Center. You guys know about the Holyoke Data Center? So 20 miles from here in Holyoke, Massachusetts it's actually called I call it the data center, but it's actually called the Massachusetts Green High Performance Computing Center. It's actually a high performance computing center. But it is a modern 15 megawatt, I'll discuss kind of power of data centers later on in the slides, data center that was opened in November 2012. It is a joint project by UMass, the UMass system, MIT, Harvard, Northeastern, and Boston University to host their computing infrastructure. So all of those universities basically have split the space and the power allocation within that data center amongst each other to host their computing. Okay. We'll discuss why it was built out here later on, but it was built out here for specific reasons.
Weather?
Say again?
Weather?
Not weather, no.
Network latency?
Any other?
Network latency?
Well, the network latency is badged to Boston, right? I mean, all the schools in Boston. The only one out here is Amherst, right? Lowell, Dartmouth, all the other UMass system schools are over near Boston, obviously Harvard and MIT. Yeah.
It has waterways to cool the data center?
It has waterways to cool the data center. Not really. It does have water, yeah.
Electricity?
Yeah, right, electricity costs is the main reason, partially due to water. But that's one of the reasons, there's actually multiple reasons. I'll discuss that later though. Okay, so yeah, so data centers going down Prashant's slides here. Yeah, so primarily, like I was saying, different than high performance computing center because we're talking about enterprises that are largely storing and processing data, internet companies like Google and Facebook. Yeah, so this stuff, data processing, websites, business apps. The key here, I think, is not complex computational simulations that you would think about that would be run by weather forecasters, physicists, computational scientists, right? Computational chemists, computational physicists, right? So simple apps, not as computationally intensive, but lots of data. All right, so data centers have been evolving quite rapidly, right? So data centers kind of didn't exist. Let's see, it was 20 years ago, right? Maybe 23 years ago or something, 95. You didn't think about data centers existing. Actually, when I started graduate school in 2001, 2002. That time, I was doing research on data centers, and I remember asking my advisor, like, where are these data centers? I had never seen them, right? And back then, in most cases, there were not data centers as physical buildings that existed like this MGHPCC. That's the acronym for the Massachusetts Green High Performance Computing Center. So it's a data center. You go out to Holyoke, 15 minutes away, you will see in the middle of town this really modern facility that looks, has these cooling towers, looks really sleek. You go into it and it's actually full of it's a big room full of computers, right? Thousands and thousands of computers. Those did not exist 20 years ago, right? What did exist were, people started needing lots of computers. So they started, taking rooms that existed and putting lots of computers in them. And then, they would call that a data center, right? In fact, I probably didn't see an actual, physical new data center until like the late 2000s or something. So they basically, over the last 20, 25 years, went from not existing to being quite large. The largest ones run by Google and Amazon and Facebook are, multiple football fields large. And actually being a fairly, being at really the center of our kind of economy, right? Like the center of the internet. They effectively the internet is run out of data centers. When you go off to a web page, you're not hitting some server at somebody's house, through their cable modem, right? That server and the software is being run out of a data center, all right? So, in the early days, what were we doing? We were just plugging in lots and lots of computers. And then, as we plugged in more and more computers, we needed people to kind of monitor those computers. Like, what were they doing? Like, how many resources were they using? Like, who had accounts on them? Who could log into them or not? And then you had to manually manage it. Say, okay, you can log into these computers, you can log into these. You'd have to add your passwords to these, take away your passwords if you're not using it, right? And there was a need to have software that could kind of more automatically provide an interface for you to use these computers, right? So then you kind of had schedulers that would run, and you would log into a master computer, And that master would allow you to submit a job. So you could have a process you wanted to run somewhere on a computer. You would give the scheduler the process, so, hey, the process is over here in my directory, and it would take that process and run it on one of the computers, pick one of the computers to run it on, right? And then it would schedule everyone's processes to run on those computers, right? And that's still one of the main modes of operation today. And then, for those kind of common scheduling frameworks, it became a little cumbersome to kind of copy your process from one computer to another, right? And copy the output of that process. Like generally you run a process, why did you run it? You ran it to get some result, right? Oftentimes with data-intensive processes, that result ends up being a lot of data. And so copying all that data around was cumbersome, especially you as a user managing all of that data. And so various clustered storage techniques arose, right? So storage area networks and network attached storage. Does anyone know the difference between storage area networks and network attached storage? What is a storage, like have you guys talked about file systems and disks? Maybe you won't in a distributed operating systems class, I actually don't know. So storage area networks are basically, and both of these provide the illusion of a common storage substrate for a large number of computers, right? So like I'm logged into some computer over here, you're logged into some computer over here, you both see the same file system. When I write to a file here, this guy over here can see that file and that it was written to, okay? That's what both of these provide, but they do it in a different way, right? So storage area networks provide the illusion of a shared disk among all of the servers, okay? A shared raw disk, so a disk, the abstraction that a disk gives the upper level system is that of blocks, right? Disk blocks that can be written on. And then on top of a disk, you write a file system that decides how to organize the data in directories or however it organizes the data, right? Network attached storage basically provides the, it's effectively a file system abstraction, right? So basically it's attaching a shared file system to all of these servers, right? So basically, from the purposes of an application, it looks kind of the same, right? There are implementation and performance differences between the two, though. Okay, so that's traditional data centers. You just take a bunch of computers, commodity operating systems, you throw them in a room, you plug them all together into this on the same network. You're managing them manually, and that gets to be a little cumbersome, so maybe you attach some network attached storage, or buy a storage appliance and have a SAN, right? So that they all can see the same file system. So if you think about it, if you all see the same file system, it makes it easy to copy data, because all you have to do, you don't have to copy data anywhere, you just read data and write data to the same place, right? So this node can, if this is the head node and you have a directory on this node that's your home directory and you have a process that you want to schedule, and you say, submit process, right? Then it can schedule it simply by coming over here to this node over here and then just running it out of the same directory. And then how do you get the output? Well, if your process just dumps the output to standard out in that directory, you'll just see it, right, whenever it gets scheduled on that node, okay? Even though you don't have access to that node, right? You can't log into it, but that node has access to your file system, right? So that's kind of the old school. Modern data centers are much more dynamic and larger, right? So not only have they gotten bigger in terms of the number of football fields and they're actually independent facilities, they typically encapsulate applications inside of virtualized environments like virtual machines, so that they're a little bit more flexible. You can move virtual machines around to different nodes to balance load. If there are idle resources on that node over there, there are no idle resources here, I might be able to move from here to there, right? The data center might move me from here to there so that I can consume those idle resources. So as a result of that, you can get much larger efficiencies. Everything about managing a data center, or not everything, but right, because all meets their, ends up in their bottom line. So if they waste resources over here, they waste enough resources, maybe they'll have to build another data center, right? But if they consume the resources efficiently, they can reduce their computing costs, right? Why do you need virtual machines or virtualized environments to move from point A to point B? You guys discuss migration? Great. So why do you need virtual machines to do that? Why can't you just do that with the static data center using a commodity operating system running processes?
Handled for failures, maybe?
No. So why can't you migrate processes around?
It's easier with virtual machines.
Well, I wouldn't say it's easier. It's possible with virtual machines. It's kind of largely impossible with processes. But why?
You have different architectures for different individual data centers.
That's one reason. There could be different architectures.
There could be one reason a system might have its own physical address. If you remove that, that's a problem.
Yeah, right. So those are two good reasons. One is architectures might differ. The other one is residual dependencies on the underlying operating system, right? So like a process, you can't just take a process's memory, user level memory, and just move to some other process because it was running on top of an operating system and it had residual dependencies with that operating system. Largely the names of various things, like the MAC address that's on that operating system. If it has any open network connections, those had labels to them, like 1 and 2, that now would be different on this other machine. File handles would have labels like 1, 2, 3, 4, that would be different on this other machine, right? So, and there's lots of those. Those are just kind of very common ones, right? And so it's really hard to actually isolate. Operating systems weren't designed that way. And so it's really hard to isolate all these residual dependencies a process has on the operating system. But virtual machines were designed that way from the outset. Right? Virtual machines have no residual dependencies on the underlying hypervisor that they run on. Because the hypervisor basically was providing a machine abstraction, right? That was independent of the underlying hardware. That was its whole point. Anyway, so this increased automation, it basically facilitates kind of this larger scale operation, right? That's much more efficient. There's many, many reasons why, as you scale up, you can get efficiencies. So here's a picture of a data center here, or like a real data center. You basically it's actually, this is, I don't know where this is from, but this is not that different than what you would see if you go down to Holyoke, 10 or 15 miles from here. They have different enclosed aisles with, this narrow aisle here with, racks and racks of servers, just from, floor to ceiling. Okay. If you think about a data center, so each of these racks, I guess, would have, basically 40, maybe less than, it had 40 slots. That's a typical size rack, is a 40U rack, where a U is basically this height and this width. And then within that rack, you have mostly servers in that one, mostly, up to 41U servers, and probably a top of rack switch. All those servers would plug into a switch at the top of the rack, and you might have a storage. In one rack, you might have a storage array that everyone, a number of racks are kind of getting their storage, network file system from. If you think about a data center and kind of what it actually does, it's, what is it doing? It is not doing mechanical work. It is not like a factory. Basically, power goes into the data center. It runs through a bunch of circuits that comprise the computing platforms that run, right? And then that generates heat, right? Because, basically energy is never wasted. It has to be, it's just converted to something else. So it's converted all to heat. And then if it gets too hot, then the servers will fail, right? So if the servers get over like 100 degrees or, much higher than 100 degrees, they'll start to fail, right? So then, it's this big room or building that generates a lot of heat from power directly and then has to cool that heat, right? And then if you want to keep it running all the time, there's a lot of specialized infrastructure in the data center to make sure that happens. So oftentimes you'll have UPSs, so universal power supplies, in the racks. So batteries in the racks get cut off of power. You'll have backup generators on site. So like at the MGHPCC, I think they have a couple of diesel generators that can power a fraction of the data center, 20% of the data center if it loses power. So you have all of this kind of electrical and cooling infrastructure that goes into powering these servers. Another type of data center is this kind of modular data center that's gotten popular. So the one thing is, you build these big facilities, and you have to kind of build them at a fixed size. And so oftentimes when they're new, they're empty. Because when a company wants to build a data center, they don't build it for today, they build it for tomorrow, right? Because they're investing tens of millions of dollars in this data center. And it's going to have a lifetime, and they're going to invest in it so that it doesn't fill up immediately, right? They're going to invest it so there's a little headroom, it fills up over time. So what that ends up meaning is that at the beginning, there's no one in the data, like there's very little workload in the data center. It's obviously highly inefficient, right? You have this large facility that's very underutilized. So there's been a lot of research into how can you make data centers, like build data centers more efficiently. So one of the ideas that has gained some traction is this notion of modular data centers. So in this case, you basically have a common cooling infrastructure. So all this is the cooling towers. These are basically air conditioners. So you build the cooling infrastructure, but you don't actually build the building with all the power infrastructure. All of that basically goes into these shipping containers and gets plugged in as necessary. Right? So each shipping container then kind of looks like, in the inside, looks like this. And then you can scale this out kind of as you need to. And the idea by the companies kind of pushing this is that you could kind of plug and play, right? So you basically as a kind of an enterprise, you don't have to go out and get an architect and kind of design this specialized data center, which is a fairly specialized facility. It's not like it's something that's cookie cutter. That's going to be expensive to do. Instead of doing that, the idea was, well, we can make these cookie cutter, right? We'll make them plug and play and expandable. So you can start out cheap and expand them as you need them. Yeah.
I have a question in the previous slide. Yeah, so these systems, okay, they have computing power and they also have some storage, right? So whenever, for example, if I'm surfing Facebook and if I click on some page, so my data goes to this place and it gets stored, right? Somewhere there. And what if, and then you say, for example, you take that part out of it. So what does my data? My data goes away, or is it being managed?
Well, I mean, generally, like for something like Facebook, there's going to be software layers on top of data centers. So, like, your data is going to be replicated across multiple data. I mean, most of those software layers are going to run across multiple geographic locations, right? So your data on Facebook is probably not stored at one data center. It's probably stored at lots of different data centers. And whenever you go to your Facebook page, that data is probably fetched from the closest data center, potentially, or the data center that can service it the best, because they're probably load balancing across data centers, right? So there's a number of scheduling decisions that likely happen when you hit Facebook, is in terms of like what data center actually serves you. And sometimes you'll see, like when you go to, I mean, I don't use Facebook that much, but sometimes, like if I post something on my laptop and then I go to my phone, which is on a different network typically, where some of these decisions might be different, I actually maybe won't see it like initially, or I might see like a different wall that I see on my laptop. They might be different. It might be, that's likely because the requests from my phone and the laptop are being treated differently, right? So they're getting processed by different pipelines. They're not exactly the same. They could be going to different data centers. Within the pipeline at Facebook, they could be getting treated differently in terms of the ads that they want to show me, or the things that they want to show me on my phone versus my laptop. I mean, I actually don't know, but I mean, those explicitly what happens. But typically, the services when you hit Google or Facebook, they're very complex and they're touching lots of servers. I think I've read. I think for Facebook, right? When you go to Facebook and you hit the wall, it's basically touching, like that request will start off a chain of, I think at least like hundreds, on the order of hundreds of RPC calls within their infrastructure. Right, to get because the data is not, like every one of your walls is unique based on your set of frames, right? And so it's not like that wall is stored somewhere like in a file system, right? It's formed for you on demand based on your friends, what they've posted, what your preferences are, and what ads they want to show you, right? And they also want to keep your interest, so they want to kind of prioritize things that they think you will like based on what you prefer. And also there's also the notion of popularity, right? They also want to show you things that are popular by other people. So there's a lot going on there in terms of like forming that up. Yeah.
So these centers seem to be like they're very active. They're dealing with data, like you're saying, a lot of RPC calls. Are there other places that don't require as much overhead and cooling that are used to like archive data that's maybe older, or is all data end in data centers?
Yeah, that's a good question. Like, are there like storage centers? I don't think so. There probably are actually. But yeah, I don't have a good feel for like for some of these industry data centers, what the ratio of storage to compute is, and if they have portions of them that are primarily storage, or maybe they even have like separate ones that are primarily storage. I think it's mostly mixed.
Okay.
I mean, it's to some extent it's hard to say because the industry data centers are their design and their contents, like what's in them and how they were designed, is generally considered trade secret because it's a competitive advantage. There's some competition as to making the data centers more efficient. Oftentimes our locations aren't well known either. Very few people work in them. They only have like, just a few employees for thousands and thousands of servers. So it's hard to like really dig into like what is really going on inside. I mean, I can just say the MGH-PCC, actually, one of the nice things about it is it's a modern kind of data center that you can like walk around in. I mean, you can't just go walk around in it, but I've walked around in it. Like some people can go walk around in it. I mean, sometimes they do tours and stuff, but anyway. And so, I mean, the way it's managed is a little more ad hoc because it's not owned by one unifying company with one unifying goal, right? And so actually there's 5 or 6 of these aisles that stretch probably like the length of, maybe not the whole length of this building, but pretty long distance. And each one is owned by a university, right? So each, like UMass has one big aisle where they can put servers. And then within that aisle, like it's very ad hoc, right? Like if I want to put servers there, I can do that. I can go and get space there and put my servers and my storage there, and other people do that too. So it's not like kind of but I have to manage it remotely, right? So they basically plug me into remote power strips that I can remotely toggle these servers. And generally these servers have backplanes where I can actually remotely log into the BIOS effectively of the server to upload operating system images, and like, if it crashes, I can pull the plug on it and reboot it, go into the BIOS remotely, and then upload a new operating system image to install a new OS or something. So I can manage them all remotely, which is characteristic of these data centers. But there's not like a unifying kind of system running across all of them because they're owned by lots of different people.
So you mean to say you will have a specific server in that, a specific computer for you yourself?
Oh yeah, so like at the MGH-PCC, I wanted to, like for a research project, I had to buy a bunch of servers. I could go and get them hosted there, tell OIT here, and I want to host them there. And yeah, I would buy my servers and I would come and put them in there, right? And then they would be hooked up to some remote power switch that I could log into and toggle the power. And I would plug, they would have at least two network cards, one for the backplane, one to give network connectivity to the BIOS, effectively, and then one give network connectivity to the actual machine.
But then how would you do load balancing if you have some particular computer?
Yeah, well, in that case, you couldn't, right? Like, so if I had 10 computers, I can't load balance across someone else's computers. Okay. Now, there is a UMass shared cluster at this data center, right, that is probably 10,000 cores or some size. You can look it up. I think anyone at UMass can use it. And it's a scheduler, like I said before, where you can schedule jobs and they will run and they will load balance. But yeah, you're right, so the MGHPCC is a multi-tenant data center, has multiple different isolated tenants. A multi-tenant data center and managing it is different than a kind of a single tenant unified data center that Google would be able to use. Google's going to be able to do a lot more kind of intense optimizations, kind of application level optimizations and system level optimizations than a multi-tenant data center can do. Right? Multi-tenant data centers can basically only do infrastructure level, facility level optimizations. They can't like move applications around. Okay, yeah, so we talked about modular data centers. So here's the notion of server virtualization. You kind of slice the server into different virtual machines such that each VM has its own OS and applications. The thing with virtualization, it provides really two things, right? So it provides the abstraction of a physical machine, right? That's different than the abstraction that an OS provides. An OS provides, what abstraction does an OS provide? I don't know. Like basically the operating system provides you a set of 400 system calls, right, that you build on top of. So you can run, on a conventional operating system, you can run non-privileged assembly instructions, right? So you can't run some assembly instructions because they're privileged, but you can run non-privileged assembly instructions, and you can make up to 400 calls that the OS exports to you, right? It's kind of a complex abstraction that you're exposed to there. So all of your code compiles down to some sequence of non-privileged assembly instructions plus calling one of 400 or so system calls into the OS, right? The virtual machine is a much simpler abstraction. It's that of the assembly, the entire instruction set architecture, right? So you can call any instruction, including all the privileged ones, right? So it gives you a machine level abstraction, and it allows you to do finely controlled resource allocation decisions, right? So you can basically allocate fractions of the CPU to different virtual machines or fractions of the memory to different virtual machines, right? So explicit resource allocation, actually. That's a good word for it, explicit resource allocation. Operating systems basically were designed for implicit resource allocation, right? By implicit resource allocation, I mean that it's not like your process is explicitly given 20% of the CPU, right? So you run, like if it's a 3 gigahertz processor, you run at 600 megahertz, right? It has some crazy scheduler in there, complex scheduler, that's trying to optimize something, right? And it's basically scheduling when your process runs versus when your process runs based on that, whatever that scheduling algorithm is, okay? Virtual machine is much simpler. It's like you get 20%, you get 20%. Someone else gets 60%, right? And it doesn't matter if, well, I won't get into that, but anyway, so the resource you get is measured and metered, right? Same thing in an operating system for memory, right? Memory allocation is implicit. It's kind of rolled into the virtual memory system, right? How you get memory and how you share memory and when your stuff gets swapped out to disk. On a virtual machine, it's generally very simple and explicit. You get a gigabyte, you get a gigabyte, right? And that's what you get, and you will always have a gigabyte. Right? Well, this is animated. Anyway, yeah, so it's showing you moving around. You can do VM migration. I already kind of discussed VM migration and why it's possible and easier than process migration. Generally, VM migration only is migrating the memory state, right? So the assumption with VM migration generally is that it's being done within a LAN, and it is not migrating disk state. So that both of these machines here, their disk would be remote, and they would share the same disk. Right, so this machine, when it moves from, I don't even know what's happening here. When this machine moves from there to there, right, this and this both have the same disk mounted. So no disk state had to move, just the memory state. When you have to move disk state, it becomes much more complex. Right? One, because disk state is a lot more, so it takes a lot more time, a lot higher overhead to move. Two, generally when you're talking about moving disk state, you're talking about being out of a LAN, right? So what's the other issue with migration when you move out of the LAN is that you're in a WAN, which is a wide area network, right? So what do you think the issue with the WAN is, migration in a WAN? Speed's an issue because you have to move the disk state. You're not going to mount a common file system or a common storage device across a WAN, right? That's going to be.
VPNs might be an issue if you're trying to move it to a different VPN than like.
Yeah, right. So IP address. You have to change the IP address, right? IP and the internet, TCP IP, it's geographically based, right? So kind of your IP reveals, at least coarsely, your location. So if you move to another location, you can't just keep that IP. That's not how routing works. You guys taken networks? Well, once you take networks, you'll realize that routing in the internet is geographically based, right? And so you just can't, pick this up and move it somewhere else. And what that means is when you move it across a WAN, not only do you have to move all the disk state, generally, any network connections that you had will break. Any network connections out to other people will break. Any connections that people had to you will break. Okay? And if you're a persistent service like Google.com, right, then people won't be able to get to you, right? So like people won't be able to open connections to you because you will have moved. So you would have to advertise a new IP address. Okay. So that's another big issue. Yeah.
When you say that the disk is shared between these two, like from the sender and the receiver, is that shared by the network or like?
Yeah, shared over the network generally.
So is it like each machine has their own disk, or is it like a common?
It's a common disk, right? So there would be another storage server that would look like this. It would look the same. It would just have a bunch of disks in it, and it would export basically all requests to write to files or disks would go to over the network to that server. In general, not all, but well, in many cases, these servers and data centers don't have local disks. There is no local disk, right? The main root disk of the machine is remote. Now they might have like some scratch local space, but it's not it's treated as scratch space that could disappear, like /temp in Linux.
But doesn't that increase the latency for IOs with the application factor of?
Sure, yeah. Well, by a factor of 1,000.
Usually disk to network IOs.
The throughput, not so much. Right, not necessarily the throughput. But the latency, I don't have a good handle on, like, is it a factor of 1,000? Yeah, I mean, it decreases the latency, that's for sure.
But you're saying the throughput remains the same? Usually even if you do disk reads over.
Well, the only issue yeah, right. So I don't want to, like, generally, like, throughput doesn't have the same issues as latency,
yeah.
right? It doesn't matter, like, how long the latency is. If you fill the pipe, the throughput's going to be the same, right? Now, you might get lower throughput because of contention on a shared disk, where you have, 1,000 machines all hitting a disk, rather than, with a local disk, you have one machine hitting the disk, right? So you might have issues there. There are a lot of, this is one reason why data center networking is a big area, right? So making data center networks more efficient is a big research area, right? In fact, one of the main research areas now is in networking is not wide area networking with TCP and congestion control. It's actually data center networking to address just these types of problems, right? And even systems research, a lot of systems research looks at how can we, mitigate some of this, how can we push storage or computation, more to or push storage more to the local machines, right? But you do have these issues, it reduces flexibility because you can't, just migrate things around like this. So here's some examples of different virtualization platforms. So VMware was the first one, right? So it came out of Stanford, right, in the late 90s. These were the first guys that figured out how to virtualize the x86, right? Why couldn't you virtualize the x86? Anyone know? Or why was it bad to do, or hard to do? So actually, virtualization as a concept, this concept was first widely discussed and implemented in the 70s, early 70s. I think it's some IBM mainframes. So people know how to virtualize processors for a long time and knew what you had to do to virtualize a processor. There's a paper from the 70s that basically says, like, for a processor architecture, hardware architecture to be virtualizable, it needs to do this, 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 and this. Okay. So the x86 didn't do that. Right? Didn't do some of those things. And virtualization back then in the 70s and like the 80s wasn't really a big deal because computers weren't fast enough, right? So like you weren't thinking about running lots of things on a computer in different virtual machines. You were just trying to run one thing on a computer like at some decent speed. Okay, so people didn't think about it too much. It wasn't a concern, right? So one of the main reasons why the x86 wasn't virtualizable is because there are some privileged instructions that you run in the x86. If you run them as at the application layer, they fail silently and they don't trap into the kernel or into the lower level. Right? That's the key reason, right? So the thing is, when you run an OS, so what's happening here is, right, you're running an operating system as an application, right? And so that operating system thinks it's at the bottom. And so it's going to run all the instructions in the instruction set, including privileged ones. So privileged instructions are the ones that only the lowest level can run, right? Only the privileged level, the privileged operating system can run. Like you might think about like reboot or turn off the machine, right? Only the operating system can turn off the machine. So some applications just can't turn off the machine, okay? That's privileged instruction. So it's running all those privileged instructions, right? But now you put it up an application layer. Okay, well, how are you going to deal with that? Well, the way you deal with it is when you run a privileged instruction, but you're unprivileged, what's supposed to happen is the machine is supposed to automatically trap you to the next lowest level. Basically interrupt your execution and then call a handler in the lower level. That will address, that will fix whatever happened, right? That will be like, why did you run this instruction? Oh, I see. You're a virtual machine, or you think you're Windows, and you think you're doing something, and I'll do it on your behalf, because I've looked and seen that you can do this, right? The other privileged instructions are like messing with the TLB, with the virtual memory system, right? Messing with the virtual memory system. Those are all privileged instructions. And Windows and Linux would be trying to do that, okay? The thing with the x86 is it would be okay if all privileged instructions that were run in the application layer are trapped into the kernel or trapped into the hypervisor, and the hypervisor could fix them. But they don't. Many of them fail silently. And as a result of that, there's no way for the hypervisor, the virtual machine layer, the virtualization layer, to fix them. It doesn't have the opportunity. It doesn't even know they ran. Right? So the way the VMware guys, the Stanford guys, fixed this by basically scanning in real time as instructions ran to see when these instructions would be called, and then explicitly inserting explicit calls down to the lower level, right? But it was super performance intensive because they basically had to scan every single instruction run and then insert dynamically, using binary rewriting, these calls into the lower level. Okay, so they did that, but they got working. Then Zen came along, and what Zen said in like 03, 04 was that this is really slow. It's really slow. Instead, what we're going to do, instead of like supporting unmodified operating systems, we are going to modify them a little bit, right? So the whole thing here was that these operating systems were unmodified. You just popped Linux or Windows down. So Zen came out, we're going to modify them a little bit. We're going to go inside of them, and instead of dynamically scanning all the code as it runs to insert these traps, when these privileged instructions get run, they actually went into the source code of Windows and Linux, and they were like, look, all we have to do is change a few things, and we'll make a few explicit calls into the virtualization layer, basically the equivalent of a system call down into the virtualization layer to get rid of those instructions. right? And then it said, by doing this, we can make things a lot faster, right? And so Zen, you know, it basically brought, it was also open source, so it brought cheap virtualization to the masses, right? So Amazon's, you know, infrastructure for a long, long time, you know, starting from 06, maybe even up to now, I think they might have switched to KVM, was all Zen, primarily because it was free. VMware was super expensive.
And how do you change Windows source code?
Yeah.
They had, well, they actually worked with researchers at MSR, Microsoft Research. And so they got some Windows source code and they changed it. That's how they did it. But yeah, that wasn't publicly available. And then around 07, 08, I think, basically, you know, you saw an instance of like hardware, software, co-design where Intel was like, virtualization's important. We should actually fix x86. So what they did was they basically created a new privilege level beneath the current like lowest level of privilege that you would trap into on these instructions. They basically fixed it, right? So like HVM, hardware virtual machine technology, different companies call it different things. But basically AMD and Intel, and they have virtualization aware server platforms now. So now you don't need these things that Zen used. And you don't need this either, because it's virtualizable now. It will trap into the lower hypervisor level, okay? You know, and then as this thing got big, VirtualBox was like you know, and Parallels was for Mac, VirtualBox was a easy to use, free, like Zen wasn't usable. It was like for data center. It was like for research, right? VirtualBox was for like normal people to want to use virtualization for free. And then KVM, which is getting kind of maybe become the dominant thing now, that was basically the Linux kernel, right? They were like, like Zen was these guys at Cambridge, like academics who wrote this and then sold it to Citrix or something. But the Linux guys, when they realized virtualization was important, they basically just integrated it directly into the Linux kernel, right? So that's what KVM is. It's kind of the kernel virtual machine. It's virtualization integrated into the Linux kernel. It seems to be the one that's kind of gonna win out here. I think Amazon might have switched to KVM. Zen is still the dominant kind of research virtualization platform just because of its academic roots. And most of the optimizations, the research optimizations in virtual machine, like migration and load balancing, have all been done in Zen. Anyway, okay. Yeah, so what do we have here? So yeah, a couple of different things. So you have virtual servers. Once everything is virtualized, it's just easier to deal with, right? Because like we talked about, you can move it around to balance load or consolidate. You can either balance load, spreading it out. You might want to do that. You can also consolidate load onto a small number of machines and then turn off servers. That might save you energy. You generally can deploy things much faster and maintain them easier. You can maintain your infrastructure easier, again, because you can move things off to do scheduled maintenance. Or if you have to like turn off a rack, you can move all the servers, the VMs off the rack and then turn them off without interrupting workloads. There's a whole range of things you can do with faster deployment, right? So you can snapshot images, right? So you can just save the entire memory state of an image, just like you hibernate your laptop, store it, and then restart it later. Anyway, and then in terms of like actually working with the infrastructure, you know, you need not have the actual computing near you, right? So you can get access using like virtual desktops into data centers where you basically your laptop or whatever is backed by much more computation than would be present in your actual laptop. It would make your desktop potentially available anywhere. Right? So a lot of enterprises use this kind of like thin client model for their workstations. Right? So some challenges. So resource management. One big issue with data centers is kind of how to, you want to, for cost efficiency, keep them as highly utilized as possible. But you have to do this in the face of fixed, kind of a fixed size infrastructure, highly variable workloads, and workloads that are potentially unpredictable. and workloads that have different types of applications that have different kind of like requirements, right? And so it basically kind of defines a very complex scheduling problem, right? It's a kind of a large area of research is how to maximize the utilization of data centers. Another big issue, which we were discussing earlier with the MGHPCC, is energy efficiency. I mean, basically, a data center is just a large, highly inefficient use of energy, right? Like it just comes in, it burns through these circuits doing computation, it's released as heat that's then cooled, right? So it's just like a hot box, that you're cooling, right? They consume large amounts of energy to the extent that, I was saying 20, 25 years ago, they did not exist. At all. Now, in aggregate data centers, the estimates are that they consume like 2 to 3% of the US electricity. So out of all US electricity consumed, the current estimates are data centers consume 2 to 3%, right? So they've gone from zero, not existing, to consuming a non-trivial fraction of all of the electricity. And they're still growing. They're actually the fastest growing segment of electricity usage in industry. Yeah.
Is that energy just to like run the computations or also to cool them?
It's both, right? So generally, rough estimate is that, and I get some slide on it later, but 50% to power, 50% to cool. That's in kind of a normal data center. Like the Google ones are much more efficient than that. So some things about the MGHPCC, one of the reasons why it was located here, there's a couple of reasons. One is that power costs are cheap. So Holyoke has some of the cheapest power costs in the state. And that's because they have a unique canal system that generates a large fraction of their power from hydroelectric sources. Right? So it's cheap power. Power in Boston is very expensive. Another reason is that that power is green, right? So it's renewable. So it's not as dirty. And so that's important to some people. And so that's another reason why it's out here. And then another reason is just actually land costs, right? Land in Boston is expensive. And so it's cheaper out here, to put it out here. Another reason is that networking from Boston to Springfield is fairly plentiful. So there's some fiber optics run from here to Springfield, or here to Boston, or there to Boston, that they could tap into. So the latency, the networking is an issue, but it's not much of an issue, right? There's good connectivity between here and Boston. And you don't need to be at the data center. Everything's automated to operate it, right? It's all remotely managed. So those are some of the reasons why. But it was mainly an energy argument, and that's why the green is in the title. So here's some typical failures in the first year of a Google data center. So one thing, there's been a lot of research on failure models or failure, dealing with failures in data centers, because once you've scaled up to 100,000, a million cores, hundreds of thousands of servers, even if failures are rare, now they're going to become routine. Like, if you have one server fail out of 100,000 per month, now you're going to have a bunch of servers failing, right? You actually probably have more than that fail. And that's hardware failures. There's also kind of software failures. So some examples of different things that can fail. Overheating. Some percentage of them will overheat due to imbalances in the cooling infrastructure. One PDU failure for about every 500 to 1,000 machines. So a PDU, power distribution unit, that's like a power strip, but like an industry scale power strip, right? So it's like a huge thing, but it's just a power strip, it's a bunch of plugs. Right? You might have to move racks, which causes a bunch of machines to be powered down. The network might have to be rewired as you add machines. So that's one of the issues, that's some of the issues in data center networking. Some of the new network topologies that people have looked at for data centers, they give you really good bisection bandwidth from like any server to any other server, but they're not very incrementally scalable, meaning that if you bring in a new rack, it's like rewire everything, And the wiring is very complex. Generally, you have multiple wires running between each machine. Scalable and efficient. It's like one area of research. But yeah, so you might have to rewire the networks, some number of rack failures per unit time, network maintenance, router reloads, router failures, DNS blips, like blips in software, domain name software, machine failures, and then hard drive failures. Thousands of hard drive failures, thousands of individual machine failures. Right? So there's a lot of research in kind of basically quantifying these kind of rare failure cases and seeing how to design systems that account for them, kind of run reliably despite of all these types of failures. All right, so here's the kind of thing on data center cost, right? So this is the question about, is it the servers or is it the cooling infrastructure? So generally, when you talk about a data center, you rate it in terms of its power. So that's why I said the MGHPC is a 15 megawatt data center. It's peak power usage. That's how many servers can actually be put into it, 15 megawatts worth of servers. Anyone know how much like an average server consumes in watts at peak?
1 kilowatt.
1 kilowatt. Yeah, that's probably a little high, but yeah, something like that. Maybe like 500 watts.
Our desktops are 300 watts.
Yeah, right. Anyway, probably like 500 or 600 watts. It obviously depends on the server. Efficiency is generally captured with this metric called PUE, power usage effectiveness. This is the ratio of IT power divided by total power. So like I was saying, the typical is like 1 to 1, right? So that's a 1.7 ratio. You have almost 2 times, what I said is 2, but you have almost 2 times total IT power divided by, or total, the server power plus the other power divided by the total power, right? So Google's more like 1.1. So what that means is that 10%, basically you take the server power, you multiply by 10%, and the excess power to cool is roughly 10% of the server power. That's very efficient. In a normal data center, yeah, like 1 to 1 is basically the server. And then this is the cost breakdown. So you see servers to actually fill it out are about half the cost. And then you have the actual power here, and then the power and cooling infrastructure are about half the cost. So the power and cooling infrastructure, so this is the power. This is actually the capital to go into building the building, amortized over 15 years. Okay, so servers are about half. Building the building and the infrastructure, like the backup generators, the wiring, that's about a quarter. The actual power to power it is another quarter. Right, so power-related costs are almost half over the lifetime of the building. Almost as much as servers, right? So servers are the other cost. As you scale these, I mean, one of the reasons why this has happened with data centers in terms of like them getting bigger and bigger and bigger is that there are massive economies of scale, right? So the bigger you get, the cheaper you can run them. Because, you know, if I have a center that has, if it's all automated, and I have some center that's like 1,000 servers, what's the cost if it's 2,000 servers, 3,000 servers, 4,000 servers? The only cost, extra cost, is the building, making it bigger, and buying more power. Right? There's no other kind of, yeah.
So has it not been discovered the optimal location? Like, because I know there's some, I work for a company that was making a lot of microgrids for data centers, and there know that you can like go to Arizona, get a lot of solar power, you can go like somewhere cold. And so shouldn't we be seeing these things pop up in the exact same types of places because of different?
Yeah, I mean, there's lots of criteria that go into siting them, right? So certainly there's an incentive to put them up north and use free air cooling. So basically like, I mean, the equivalent of opening the windows. It's more sophisticated than that, but like at the MGHPCC, they have cooling towers. So they have, you know, these big towers that have water in them that basically are cooled or heated by the outside air, and they're actually, that water is used to cool the facility, right? So like if it's a really cold day, then they'll have really cold water, right, that they can run through. And water cooling is more efficient. But the equivalent of like putting them outside. So north is better, obviously. But then there are other things that come into play, like you want to be close to customers, right? So you can't just not be in LA because it's not far north. There are a lot of customers in LA, right? There's also access to transmission lines. They require a lot of power, right? So you need the power. You got to generate the power. Where are you going to generate the power from? So a lot of them are near dams, hydroelectric facilities like Holyoke. The Columbia River in Oregon is where Google has one of its larger data centers. You also need the grid power infrastructure. So actually, there's a move to, I think Google's most recent data center was built in northwest Alabama at the site of an abandoned or a defunct coal plant, coal generating plant. And the reason why is because it already had the transmission lines in, the power transmission lines built, and it actually had two grids. So two separate transmission lines and two separate grids, because this was a generating plant that was like providing power in the past. So that infrastructure was already there. So that was one important like criteria in that case for siting it there, is that it serves as basically backup power. That like I'm hooked to two grids. If this one goes down, I got these guys over here who can still supply me power. You know, so yeah, weather goes into it a lot, but it's also customers. Solar power, you know, solar's great, but it's always in hot places, right? So there's a trade-off there, right? Anyway, yeah, so the big economies of scale, you know, so we keep getting bigger and bigger and bigger. You think that, you know, there might reach a time where it's like the trend might stall out. It's unclear like when it will stall out in terms of like when do you reach the economy of scale where it kind of gets less efficient. I don't really know. The push towards smaller data centers is really about kind of pushing close to the customer, right? So like there's always the latency issue. You always want to be closer because you can't go faster than the speed of light. So this has helped grow the popularity of cloud computing. So basically the cloud basically is kind of hosted in data centers. The cloud is a lot of stuff. Everyone has their own kind of thing with the cloud. I would characterize it with these four different characteristics. Remotely available, right? You're accessing data centers. You pay as you go. You pay for the computation that you're using, the cycles that you're using, the storage that you're using. You can scale up very fast. Right? So you don't have to plug in a bunch of machines to scale up. You can scale up to the infrastructure, and it's shared with a bunch of people. Right? So all of you guys can go off to the cloud and get resources. Different types of services in the cloud stack. At the bottom, infrastructure as a service. Amazon, I don't know why AT&T is there. I guess they have infrastructure as a service. Really, Amazon, Google, and Microsoft are the three big IaaS providers. This is kind of what I've been referencing throughout, right? You go to Amazon, you can get a virtual machine. You can rent a virtual machine and access it remotely, you know, via remote desktop or SSH. And you can get 1,000 virtual machines or 10,000, or however many you want, at roughly a cost of maybe $0.01 an hour. Okay. And the same thing with storage. You can go out and get however much storage you want in the form of disks that you can access remotely. Raw infrastructure, platform as a service are basically software APIs that you can build on top of. So you can think about it like an operating system. You build on top of the system calls, but these are different types of APIs that are targeted for specific applications. So like Google App Engine is targeted for web applications. So if you want to deploy a dynamic website or web application that does some processing on behalf of web requests, you can build it on top of Google App Engine. It's a higher level of abstraction, right? It's not raw resources, it's APIs, function calls you build on top of. Okay. And then software as a service, or actual applications that have already been built, generally using platform as a service, right? So like Gmail or Salesforce. In most of these cases, this is a stack. So like the applications here might be, you can think about being built on these APIs, which are then hosted on these servers, right? In fact, Amazon, I know, like internally, eats its own dog food in the sense that that's how they build it. Like, Amazon's not only a provider of infrastructure as a service, it is a user of its own infrastructure as a service. And in fact, the reason why Amazon kind of invented the cloud back in 2006 is because they had highly asymmetric resource usage, right? So they had all of these computing resources, and they bought them all so that they could process their peak demand at Christmas, right? But then Christmas went away, and then all of their resources would just sit idle, right? It was like, let us sell these resources to other people that can then use them, right? And so actually at Amazon, Amazon does everything, right? So they compete with everybody, Netflix and Walmart and Google. There are all these things, but so they're like 1,000 businesses. All of their businesses use their products or use infrastructure as a service just like you do, or just like you might, or you could, right? The same probably generally true of Google as well, and the other ones. So yeah, this is actually a stack. So yeah, EC2, an example, right? So this is their IaaS example. You can go and you can look, there'll be a big menu of like things you can buy, how many CPUs it has, what its RAM is, what is its price, what's its storage, what's its bandwidth it offers. There's a price on everything. It's actually way more complicated than this, right? So there's like dozens of geographical regions and available like data centers you can choose from. There's 50 to 60 different types of VMs you can buy. It's just small, medium, large. And they sell them under a bunch of different contracts that kind of are somewhat complex. Some of them have a fixed price. Some of them have a variable price that's dynamic. It's, there's a lot going on there. Google App Engine, basically it kind of automatically scales out like web applications if you build on top of their API, so that if you get more web requests and you provision for on your set of servers, it'll automatically go get more servers for you. It is not based on virtualization, so multiple threads potentially run in the same OS, right? So there's less protection between different customers inside of App Engine. But it allows Google to kind of scale things up really quickly. So it's narrower. That here we can do anything. You just get a server, we run anything. Here we can only run what the abstraction provides us, what the APIs allow us to do, right? So it's much more limited, narrow class of applications, basically web applications. Okay? And then in this case, the bindings are only in Java and Python, so you're also restricted to the language. So those are public cloud examples. There's also this notion of the private cloud. A lot of companies aren't into public clouds because they maybe have rules like health companies can't put your health data on Amazon. Some of that stuff's starting to break down. Like public cloud platforms are getting more and more mind share. But a lot of companies still have these kind of private clouds that they maintain, which kind of look like Amazon, but are in private data centers, where they kind of do the same type of thing. And you also see hybrid models where you kind of have both. You have some private cloud, on-premises infrastructure, and then if you need it, you burst out into the public cloud if you need to scale beyond the resources that you actually have locally. Different programming models, so client server, just like a web server, right? It's a request-based. You have some web server, you have clients that ask for state or ask for computation. Batch processing, so this is like kind of scheduling, job scheduling that I was talking about before. Non-interactive, right? So this is generally interactive. This is non-interactive. This is scheduling processes on machines, right? So that they're highly utilized. And then MapReduce, another kind of big data processing. It's like batch processing, same thing at a high level. It's non-interactive processing, running processes, scheduling processes on nodes. But generally what they do is they provide a slightly higher level abstraction that constrains the application, but kind of defines in a way that allows them to automatically scale it out, right? So with MapReduce, you basically have this map and reduce paradigm where you first basically filter a bunch of independent data streams that can be done in parallel, right? And then you reduce it. So you basically have all these independent data streams that have been kind of filtered over, and they all get combined, and then you run kind of a common filter over the combined data streams, right? That's kind of the paradigm of the MapReduce application. What that allows it to do is basically it can run in parallel that map phase, right? And then the reduce phase can also basically start running before all the maps are done, right? So it's kind of like this parallel job of a certain format that runs, and it happens that that type of job was very common at Google, which is why they came up with that. Let's see, am I almost done here? Yeah, okay, so some future challenges, privacy and security. How do we guarantee isolation between client resources? This is an issue in the cloud because you're sharing the infrastructure with everyone else. As we scale up, how can we manage all of these servers? Like what kind of failures will arise as we continue to scale up? And what kind of programming models are effective as we scale up? So it turned out MapReduce was very effective, more effective than batch processing because a large number of applications kind of could be constructed in this MapReduce format, which allowed it to automatically parallelize computation more than just a simple batch processing system. And then here's some references, right? So this is a good overview paper, survey paper on cloud computing from Berkeley. And then here are the relevant conferences. So hot topics in cloud computing, short workshop papers, SOC, symposium on cloud computing, kind of the main cloud conference. And then systems conferences, NFDI, Uthnix, OSDI, and SOSP will generally have a session or two on kind of cloud stuff. And I am 2 minutes over time, and that is it.